Okay, I think we can probably start. Most people have had the opportunity to join. So welcome. Welcome to the AI for Health webinar. So for those of you that are joining us for this first time, this is a monthly event that was originally in person, then turned into a virtual meeting. And the goal is to invite researchers and entrepreneurs that are working at the intersection of AI, healthcare, and life science to discuss some of their work and get their perspective on this field. You're welcome to check our Eventbrite or Meetup page. That's where we announce a future event. And again, we try to do them on a monthly basis. So just keep an eye open. So I'll introduce myself. I'm Sebastian. I'm from InVivo AI. We're a Montreal startup that brings efficient AI algorithms for small molecule drug discovery. And I'm joined today with my co-host, Sophia, who runs AI for Health News. That's a newsletter that provides bite news for AI in healthcare. And I invite you to check our newsletter and subscribe if this is of interest for you. Today, we're going to have a slightly different format than our usual webinar. We're going to have a shorter presentation. It's going to be roughly 15 minutes, presenting some of the work in AI for preserving privacy-preserving application. And we're going to follow with a longer than usual discussion with some questions. And that's where I think it's going to be interesting for everyone to contribute and ask questions through the chat, which we will do our best to cover at the end of the session. So please keep your muted during the presentation just to avoid any unwanted noise. And I'll let Sophia introduce our guest for today.
Okay, great. Thanks, everyone. So it's my pleasure to introduce Dr. Baron Cases and Dr. Pasrat Pombach to our webinar. We invited them just a few weeks ago to speak at the webinar, and they were very excited to take part and suggested to do a question-answer format. So we're very excited to have them on board. And just to tell you a little bit about their background and what they do. So Dr. Baron is an adjunct professor of radiology and senior attending radiologist at the Technical University of Munich. He specializes in abdominal imaging with a focus on pancreatic cancer imaging. His research focus lies on the development and clinical translation of novel imaging methods and the medical image analysis algorithms, as well as on the integration of multi-parametric clinical and imaging data. Dr. Cases is a specialist diagnostic radiologist at the Technical University of Munich. He is a machine learning researcher at the Imperial College London and a research scientist at Open-Minded. His research focuses on probabilistic methods and differentiable programming, as well as on the design and deployment of robust, secure, fair, and transparent machine learning algorithms to medical imaging workflows using next-generation privacy-preserving machine learning methods. And Dr. Pasrat Pombach is a research scientist at Consensus Health and Imperial College London. His research focuses on privacy-preserving machine learning and decentralization. He is exploring the potential of bringing together techniques such as federated learning, secure computing, verifiable computing, and blockchain to build a new generation of healthcare systems. So we're very happy to have you here with us today, and I'll let you take it away from here. Thanks, everyone.
Thank you very much, Sophia. I hope everyone can hear me. Let me just give you a brief roadmap of what we'll be covering today. Me and Jonathan will give an overview of the most important concepts, techniques, and challenges, trying not to repeat the material from the paper too much, which you will find linked, but we'll also have it in the last slide if you haven't read it yet. Also, we've prepared some Q&A discussion material, and obviously we'll try to address some of your questions as well. So since you're all here, I presume you all know that we live in the age of AI, which lives on data. And whether we like it or not, we spew our personal data everywhere and all the time, for example, when we use the web. There are, however, sectors, and healthcare is the most intuitive one, where this kind of data sharing is unacceptable. And this situation creates really an unsolved dilemma, which is, how do we bridge the gap between data usage and data protection? And The standard in medicine so far has been to aggregate data, share it among institutions or researchers, and process it in anonymized form. And I've put anonymized in quotes, and I'll explain why in a second. So anonymization is essentially trying to remove all the personally identifiable information from data sets. It turns out that there's no such thing as anonymization in reality, and it also might be that patients themselves or researchers don't really want to transfer or centrally store data. And the question we therefore sort of have is, how can we answer questions using data which is not available to us directly? The other side of this coin is the desire to protect data from unwanted disclosure. And I've put this XKCD comic here, which gives an example of data leakage from a predictive keyboard system. But we also would like to protect data from deliberate attempts at theft or manipulation. And the same also holds true for algorithms, which are intellectual property. And they should therefore be protected against this multitude of attacks and insecurities. And you might be wondering why I've included this sort of innocuous looking Twitter password reset page here. And this shows a very uncomfortable reality, which is that in some countries, being a Twitter user is actually a crime. And if you use this telephone number-based reset option, you can actually use it to test with only one bit of data and compromise the security of another human being. And so this shows sort of how deep-reaching and far-reaching these considerations can be, and how easy it is to compromise an individual's privacy. So the field of secure and private AI is very multifaceted, and it's also very interdisciplinary. It starts out by sort of thinking how to safely store data, reduce the sharing requirements, and how to build systems that are both secure and privacy preserving, and also preserve confidentiality. That is not only the control of personal data, but also the secrecy of personal data. And such systems, however, need to be able to be trusted. And we want to make sure that they're trustworthy by providing options for everybody to audit them. And the goal that we're following is to retain ownership, governance, and sovereignty over the data and the algorithms. And the reason for that is that these have now become really production relevant goods and have substantial monetary value in many cases. I'll briefly show the figure that we included in the paper, and it shows an overview of the techniques which we'll briefly touch upon, that is distributed computation, encrypted computation, and differential privacy. And healthcare is a really great field in that regard, since all of the techniques are applicable, but in general, they're equally applicable to a wide variety of other scenarios. They're also, I have to say, being developed at really a breakneck speed. So what we are talking about as the state of the art today is probably ancient knowledge by tomorrow. The technique which probably many people have heard of, or some people have heard of, and is probably the most, which has been talked about the most prominently, is federated learning. And federated learning is a method which enables for the data to stay with the owners and the algorithms to be sent to the owners of the data. And in this example, the model's owner sends the data to Joe, and Joe trains it a bit and sends it back. And then we send it to Jane and Jack, and they each train it a bit more and they send it back. Now in this example, we shared the model with Joe only at the start and with Jane and Jack concurrently in the second step. And federated learning gives this flexibility of how models are being passed around, which we also call the topology of the federated learning system. It, however, also requires a lot of network traffic, which is an impractical issue, especially with very big models. So we need to start thinking about optimization, quantization of models, reducing the size. We also need to think about whether Joe and Jack are always going to be online to give back the model after training. It's also quite challenging to make sure that the data the three of them have is of high quality, it's representative for the collective that we're trying to train upon, it's balanced, etc. And we also need to make sure that we can find a way to fairly track how much each of them contributed to the training process as a whole. Then there's the question, what happens if somebody hacks into Jack's computer and starts messing with the model before sending it back? So it turns out that all in all, federated learning is a tool for distribution and decentralizing computation, but it is in itself not necessarily a privacy technique if we don't add any additional security. And this additional security can be provided by one of the following techniques. Differential privacy is both a concept and a set of techniques. And differential privacy makes it possible to reason statistically about a data set without the disclosure of data from an individual party. So the concept of differential privacy is inherently such that it tries to formalize the notion and the notion of privacy by making it measurable and providing each individual with a certain scope of interaction with the data set called a privacy budget, after which they're no longer allowed to interact or make dataset queries, for example. And the way this is conceptually done is by adding statistical noise to data, which is, the point of that is to obfuscate the individual while allowing statistical operations on the dataset. And this is actually quite an abstract and complex idea, so I'll try to illustrate this with an example. Let's assume that you're trying to, as a researcher, find out how prevalent a socially unacceptable behavior is in society. You obviously can't go asking people whether they are performing this unacceptable behavior, but you can try to find an average of people who do it by doing the following. You give each of them 2 coins, and you ask them to go in a place where you can't see them and flip both coins. And you instruct them that if the first coin falls heads, for example, they will tell you the truth. But if it falls tails, they will answer based on what the second coin came out to be. So by doing that, you give them what's called plausible deniability. They can always say, it wasn't me answering, this wasn't the truth, this was the coin. They can sort of, hand over responsibility to the coin. But at the same time, you know that statistically a fair coin follows a binomial distribution, which is now overlaid over the data. And by removing this distribution, you can still make statistical judgments about the mean of the data or some other moments of the statistics, while removing the individual's contribution from it. Differential privacy is a very new field, and it comes with really tough challenges. For example, it's very difficult to translate between this theoretical measure of privacy, the privacy budget, and meaningful business metrics. There's also a variety of methodological implementations being developed for different use cases. For example, adding noise before sending data to a cloud, for example, on wearable devices, which is local differential privacy, or adding it on a database, which would be global differential privacy. And these have to be decided and sort of weighed against each other. And like any privacy algorithm, there's a utility between privacy and accuracy. And we're still not completely sure how to deal with this privacy utility trade-off in specific data. And medical imaging data is a great example for that. Because if you just go around adding noise to medical images, they will still be images. So noisy images are just images. And we need to find smart ways to integrate data and differential privacy into this kind of data, which is not necessarily structured. So I'd now like to hand over to Jonathan to talk about encrypted computation and also talk about some of the open source tools that we're developing for making privacy preserving ML usable.
Thanks, George. Can everyone hear me loud and clear? Yep, perfect. Okay, let me just share my screen then. Can you all see my screen? I can't see you anymore, so I just need like an oral confirmation.
It's perfect. Go ahead.
Okay, perfect. Okay, so if you remember the diagram that George showed at the beginning of the slides, where you had this difference between what techniques protect the input privacy versus what techniques protect the output privacy. So the differential privacy is a good example of what protects the output privacy. And the ability to perform encrypted computations, as I'm going to talk about in the next few slides, is more concentrated on how you deal with preserving the input's privacy in the context of machine learning. I'm pretty sure that everyone is very familiar nowadays with the concept of encryption, and we mostly think about it with two things: what we call encryption at rest. So, for example, when you have a storage, your hard disk that is encrypted, or some files on your disk that are encrypted. We also think about encryption in transit, with SSL being like the most obvious example that allows communications across the internet to remain encrypted from one point to another. But what we are going to discuss today is encryption at use. So when the data is being processed, the ability to let them encrypted, let them in a black box that we can't see, and do what we call blind computations. So for that, there's a bunch of different techniques which all have their pros and cons that we go over. Some providing theoretical guarantees and implemented at the software level. And these are homomorphic encryption and secure multi-party computation. Some other techniques are provided by the hardware itself, and that's mostly secure enclaves, also known as trusted execution environments these days. And we will see how these can be combined with what we call system level guarantees, and that's provided by the emergence of distributed systems like blockchain that make a long use of cryptographic techniques as well. So homomorphic encryption first is basically what the cryptographers call the holy grail of what they would like to have in real time. The idea is to encode the data that you have in order to be able to perform computations on encrypted data, just as if they were plain text. So basically, you want to be able to do 2 + 2 = 4 on encrypted 2 + encrypted 2 = encrypted 4. This has been theorized in the 70s, so quite early on. But the first demonstration of a fully homomorphic encryption system only came about 10 years ago in 2009 in the PhD studies of Dr. Gentry, who basically proved that if you can encode your own decryption and an extra gate in an arithmetic circuit, then you could basically encode any circuit, and that's what we called fully homomorphic encryption. This ability to perform arbitrary computations. This, of course, doesn't come for free. We'll see that there's a strong overhead in the computational requirements when you try to do homomorphic encryption, and it comes in two aspects. You have the overhead in terms of what you can compute in real time. Like to give you a rough idea, some schemes can only process gates at about 13 milliseconds per binary operation. So that's basically the performances of a computer from the 80s. So it's not really good for the kind of applications we want to do, especially in medical imaging. But you also have like very strong requirements in terms of memory. For those who are familiar with some very common models in ML, MobileNet, for example, there are some implementations using homomorphic encryption that use about 150 gigs of memory. So for a network that is designed to run on edge and mobile devices, that's not really the kind of hardware performances that you can expect from there. The main benefit though is that you're not expecting anything in terms of cryptography from the hardware you're running onto, and you're not involving you don't have to trust any third party to run this thing. So that's why it's the holy grail in a sense. Another protocol, multi-party computation, another family of protocol, let's say. It's the idea that you can split a computation between different actors, and none of these actors will have a view on the entire data, so that they won't be able to learn or to see a potentially sensitive piece of information, but will still be able jointly to compute a function on this data. So a very simple example that could be what we would call additive secret sharing. So it's a very simple MPC protocol. Imagine you hold the piece of data 5. You can split it in 2 shares, 2 and 3, and you can give it to 2 other parties. I'm going to try to highlight that with my pointer. Yeah, you can give it to 2 other players that will run the protocol for you and run the computation. So of course, if you're just being given a 2 and a 3, you have absolutely no way to figure out what is the real value that is hidden behind these 2 and these 3, unless these 2 parties collude together and they can reconstruct the original piece of information. In general, you would of course implement something much more complex to prevent these kind of things from happening, but that gives you the idea of none of these parties can do anything on its own. So that's why we refer to that as a shared governance scheme as well, where not only the computation can only be done by multiple parties together, but also the decision to do something on the data has to be done in agreement with the parties holding the shares. And that's something very powerful because it can go beyond purely secret computations, but can also be used to implement advanced protocols for the governance and ethical uses of machine learning models. And so yeah, these kind of schemes also, as the homomorphic encryption one, allow you to do computations without revealing the data. And because it's additively homomorphic, the decryption, in this case, the recombination of the shares by the original data owner, give you the result you expected from the original computation. There are a few challenges to these protocols, as we've seen, like the computational requirements are one, the speed, of course, if you have real-time constraints, but of course you also have to make compromises in the way you implement algorithms. So one thing that we've not really delved into the details is how you make these things happen, how you translate a machine learning model or training procedure or an inference procedure in this encrypted world. It's not usually a one-to-one mapping between the operations that you can do in plain text and what you can do in the encrypted world, which can lead to some numerical instability if you don't pay attention, and some losses of precision as well on the result. But usually that's something you can handle with trading off for speed, for example. Some protocols do involve trusted third parties, but you can make the choice to use them or not, depending on the applications you have. And something that is very common as well in the world of cryptography is how do you consider your adversaries? How do you consider the participants that could, for example, be dishonest in running the protocol? Most of the times you have two main categories. One that is called semi-honest, but also honest but curious, which means that all the participants will follow the protocol rigorously, but might try to learn some information out of it. So if your protocol is resistant to this kind of adversaries, it means that you have the guarantee from the protocol that the information in the data won't be learned by a dishonest participant. On the other hand, if you have a malicious participant, then the attacks that it can perform are much more powerful, and it can actively try to harm the protocol in order to either disrupt it or to extract some information out of it. So it's much more challenging. Not all the protocols are providing this kind of guarantees, and usually it comes with an even higher overhead in terms of computations. This is mostly true, all we've been discussing for the inference time, so for what we call secure inference, because training on encrypted data is even more challenging. So it brings challenges on its own, because most of the optimizations we can employ, we can leverage in order to accelerate secure inference in the encrypted world, are not available at the training time. I'm thinking, for example, when you do inference on your network, you know the weights, you can perform quantizations, and all these sorts of kind of techniques that we know from the ML literature, and that's why training is more challenging per se, aside the fact that it requires more operations by definition. Which is why something that is very popular these days is utilizing hardware level security. So something called trusted execution environments. You can think of them as basically the blank tile that you have in the game of Scrabble, where you can use it to fit whatever purpose you want, whatever letter you don't have in your set. Well, that's the case with trusted execution environment. They are less constrained than the other ones in terms of what you can implement, and also much easier to leverage. With the current software stack that we have and the development that have been made in this direction, as you can see, for example, with the recent confidential computing offering by Google Cloud, you can pretty much take your existing machine learning data science stack as is. So literally think Python, PyTorch, TensorFlow, whatever you want, and bring it very easily onto these kind of environments, and having the same kind of guarantees that you would have with the software level cryptography. So it's more practical, more developer friendly in a way, while still guaranteeing total confidentiality on your data and on your model during computations. Of course, it's not perfect, as I think we're discussing today. You're basically putting a lot of trust in the vendors. So some people are not comfortable with it. You also need to have the specific kind of hardware available, even though some of the TEE's trusted execution environments are now widely distributed. I'm thinking, for example, of the Intel SGX that is, I think, pretty much widely available in all the Intel processors since 2017 or 18. But it has been suffering quite a lot of attacks, side channel attacks like Spectre and Meltdown that you might have seen going in the news. Also, another concern is if you don't have a machine that is TE enabled, are you allowed by regulation to move data to a server that is, which might or might not be true depending on the jurisdictions under which you're operating and the kind of data you're processing. And another challenge I would say with the TEs is that they are functioning on CPUs nowadays. There are ongoing research by the main hardware vendors and other entities to bring the same kind of a hardware level cryptography on hardware accelerators like GPUs. But today, if you want to leverage a GPU in conjunction with a CPU TE, you have to come up with further protocols to get the two of them work together while preserving the privacy of the data. Now, moving on to some software frameworks, I'm going to focus only on the frameworks provided by the OpenMind community. So for those who don't know, OpenMind is a very large open source community that gathers about like 7,000 people on the Slack, probably lots of others that are involved, but not present there. So it's a very vibrant and dynamic community. He's now about 3 years old, I think. And that came up with a bunch of software tools to make all these privacy preserving computation tools easier to utilize in the context of machine learning. So the main targets for that are data scientists that know machine learning and know how to deploy and develop new models, but don't necessarily have any background in cryptography or in advanced stats and all this kind of techniques that compose privacy preserving technologies. So PyCit, for example, which is the flagship project from OpenMind, supports PyTorch and TensorFlow. And through these abstractions of PyTorch and TensorFlow, provides implementations of multi-party computation, federated learning, building bricks, also more recently homomorphic encryption and differential privacy. So it's literally being able to leverage all these very advanced techniques that we've seen without having to worry about how they work and having to re-implement them, which can be very challenging. To make this work in a networked environment, OpenMind also proposed the PyGrid framework, which is designed to organize different data entities and to be able to discover both data and models across a network of nodes that would be able to either share their data, share their model, participate in a federated learning network without having directly access to that data. So you can think of very advanced use case such as, I am a data scientist, I want to train a model, but I don't have the data, so I'm gonna search the PyGrid network to figure out whether other entities have the data that I'm requesting. And these entities can implement very fine-grained policies to allow me or not to have access to the data just for training. So again, it's not about downloading the data, it's about using the data for training or inference without really seeing them. And with that, I'm going to hand it back to George for a quick conclusion on this presentation.
Thank you, Jonathan. So it's obviously a huge topic to cover, like in half an hour, but I think the take-home message is mainly that the whole field of secure and private AI is trying to make sure that the conflicting interests between data usage and data protection don't become a zero-sum game, where one party's gain becomes another party's loss. And we try to do this by creating trustworthy and safe technical systems. And obviously, such a new field, which is also so multidisciplinary and broad, will profit hugely from you guys. So, and from everybody else who's going to listen afterwards. So we think that it's really important to educate people and to have the scientific and the political and the ethical and the societal discourse about the value of privacy. I think the COVID-19 crisis was a wonderful example, a terrible, but in a sense, very interesting example of how privacy sensitive topics can affect us. And on the other hand, a wonderful example of how interested people are in their own privacy. And we also think that there's a dire requirement for academic research and industry research for on these kinds of techniques and methods. And obviously we're working on creating open source tools, which we want to provide for everyone to use. And we would love for people to contribute and join us. So you can read about all of these techniques in our paper, which we recently published, and you'll find it linked in the invitation and also probably in the recording. And I'd encourage and invite you to all get in touch either via Twitter or on the OpenMind Slack, which has 7,000 members, but there's no reason why there can't be a few thousand more. So with that, thank you very much. And I think we can enter into the discussion. So I'll hand it back to Sophia and Seb.
Super, thanks. Thanks for sharing these great techniques for secure and privacy preserving AI. It's very, very interesting. I'm wondering, for the healthcare sector, what would you say makes the healthcare sector a bit different than other privacy sensitive sectors that are out there right now?
So maybe this is a question I could answer from a medical point of view. So when I entered into medical practice, I had to take an oath, which means that I will protect data and information passed on to me from patients. And this makes it really part of my job to make sure that this is really taken care of. And I think the main or the big issue is that it's really a privacy breach in this area has impact on almost any aspect of a patient's life, from social areas, ethical issues that so all of a sudden your colleagues know of a particular disease that you have, all the way to financial impact because your security company is does not want to take you on. And so this makes it, I think, very special and very high value that we must protect. And then beyond that, I think there are a couple of specific issues related to the data that we're dealing with. On the one hand, it's very homogeneous compared to other data in the medical field, for example, when we're dealing with imaging data, but then when it becomes more complex, and I think in AI, we generally don't rely only on imaging data, but we want to develop algorithms that can be of use in helping patients. We need their other data, and this is highly unstructured. So it could be handwritten reports, unstructured reporting, ECG data, lab results. All this comes together and makes it very complex to deal with.
Okay, thank you. And so if we think about more specific applications or real world kind of use cases, would you be able to give some examples of how this is being applied, whether in healthcare or otherwise, for privacy preserving AI?
I think we're just at the start of this, and there are some initiatives. For example, in Germany, we have this consortium called Joint Imaging Platform, JIP, which is financed by the German Cancer Consortium. And this is a perfect environment where several university hospitals teamed up, invested into hardware at each site, and is using this system to specifically enable, for example, development of algorithms by federated learning. There's another initiative which is now just thanks or in response to COVID-19 pandemic being released, and it's up for evaluation, but this is an initiative that will connect all university hospitals in Germany. So this will be a perfect environment to further develop these techniques. And of course, there's also international examples. For example, Jonathan's home university is part of this initiative, the MON AI, between King's College and the ICL. And this is another example of real world implementation of the environment to enable such techniques.
Great, thank you.
So I'd like to follow up with maybe a question regarding, so in the medical domain, it's especially important that your predictive model is fair, given the heterogeneity of the population, and also how do you make sure that how do you make sure your model is fair, and how can you interpret your model if the data is encrypted, for example, and you can't see it?
Yeah, so I think that's actually a very important point you're touching upon, and one which isn't yet truly illuminated in the literature. So there's work which is just starting out to be published, and we've got some collaborators in OpenMind, and we're working on things like this at the University of California. San Diego is doing a lot of great work on this, for example, and I can link some papers to include in the material afterwards if people are interested. Mainly, I think the simplest way to obviously do this kind of thing would be to evaluate the model on new data, and to try to make sure that you're getting the intended results. But I think that this is only, sort of a marginal use case, and there will certainly need to be a lot of research into privacy-preserving interpretable models, and that will also sort of probably create a new sort of let's call it give and take between privacy and interpretability in the same way that we have between privacy and accuracy, I guess.
Thank you, very interesting.
Yeah, and what would you say are some of the biggest barriers to adoption of these techniques?
So for one, maybe this is also for me, this question, interdisciplinary expertise, I think, is really needed. I mean, this is the combination that is required here from people coming from the medical field who have insight into real world problems, which I would consider myself to be one example of. People like George, who are exactly on this interface between radiology and informatics, IT, and people like Jonathan, who are deeply rooted in the very basic development of such techniques. And this is really something that is absolutely required. And then when we're coming to the data and the dealing with the data, What we, from the early days in AI development and imaging, for example, learned is that we would, or what we applied, we tried to homogenize our data and to make models work well on these data sets, and we could generate good results. But then with the time when we release these to more heterogeneous data sets, or data set were acquired on different scanners, for example, models wouldn't work so well. And of course, we have to make sure that we do not detect different vendor scanners rather than different pathologies. So this is one big issue. When you do deal with multiple parties, of course, you have the issue of quality control. How do you make sure that at different sites, the entry data is of the same high quality, or at least comparable to the quality that you're providing? And then, of course, it's highly demanding, as I said, from the interdisciplinary point of developing these techniques, but then also in terms of applying them. We're just building this up at TU Munich here. And of course, this requires a lot of interaction with our local IT people, which is also challenging because they also need this expertise to be able to interact with our group.
That's very interesting. Thanks.
I think it's interesting you mentioned that interdisciplinarity is one of the key potential limiting factor in adoption, and I guess this was part also of the motivation of creating this meetup, is to bring people from the AI community and also from the healthcare sector. So I think it's a nice segue to this. I think it became, at least to me, it's clear, and I think it's also clear to the audience that increasing data sharing and access will eventually create more impactful AI technology in the medical sector. And can you comment on whether some of the strictest privacy-preserving techniques have an impact on predictive accuracy of the resulting model? And in other words, is there a trade-off between privacy and accuracy?
Yeah, absolutely. I think this is very worth pointing out once again, that this is a very, very real limitation that we are still facing at the moment. So both Joe and Rikma both talked about two different aspects of this. One is the data that we're dealing with, and we really need to make sure that we rigorously quality control the data, that we make sure the labels are balanced, that the classes are balanced, or if they're not, that we account for that. And this comes with huge challenges. For example, the class balance of a data set is in itself a potentially privacy sensitive characteristic, which we cannot share. So we need to find privacy preserving ways to control for it. So the data is one big reason why there's this privacy utility or privacy accuracy trade-off. And the other one is inherent to the methods that we use. And as Joe mentioned, there's a lot of numeric approximations going on. There's issues where when you create deep networks, for example, and you polynomially approximate activation functions, they become unstable to a point where you can no longer converge your network. And there's a lot of problems, of course, with sharing networks over the data network. I mean, now, and sharing algorithms over the data network, which are very big, which limits their scope of use. So it is full of trade-offs at the moment, and I think that that's the reason why we need this sort of intensive and focused research.
Thanks. I think it will be interesting to see how over the years this trade-off actually shrinks and can achieve similar accuracy while preserving privacy.
Definitely, I think
yeah. Thank you very much.
Like huge strides in this as well, and like the state of the art is really advancing very, very quickly.
Yeah, definitely. And I think all of these techniques are moving forward in the right direction. And if we think about other frameworks for federated learning, and specifically about the SODA technique, would you be able to tell us a bit more about that?
Yeah, I think I can take that one. So of course we've discussed the OpenMind community and PySIF, but there's other people building things. If we mention the big names, you've got Google and Facebook have their own frameworks. There's TensorFlow Federated, TensorFlow Privacy as well, if you want to use differential privacy with your TensorFlow. And Facebook Research came up with the Krypton framework that implements multi-party computation as well. That's being bridged into OpenMind as well. So OpenMind could be kind of like this unification platform where you can use all of these techniques in one place without having to choose. In terms of pure federated learning, there is a lot of extremely good work that is done at WeBank in China, and they have the FATE framework that is, as far as I know, one of the only production-ready federated learning framework that you can literally deploy on the cloud using all the DevOps things that companies are using, Kubernetes, all these kind of things. And they're also extremely active in the research space on how to move lift all the barriers that we've discussed. So definitely worth looking into what these guys are doing there. There's also these are all open source frameworks, by the way. Absolutely nothing proprietary. The last one I would like to mention is probably Substra, because it's close to also one of my research interests. Substra adds one thing that is not present in the others. It's this aspect of traceability and auditability by using a distributed systems, a blockchain in that case. Even though that's not a public blockchain, so it's we can argue whether or not it's very transparent. But for consortium use cases, I think it's a very good achievement as well.
Super, thanks.
Great. So I think we have a couple more minutes, and we have a couple questions from was shared to us beforehand or in the chat. So I want to make sure we take a bit of time to answer these. So Anton in the chat asked, what about using CycleGAN or a similar generative model to translate the style of a subset of the image to see how they typically look like without seeing the real data? So could you comment on this?
Yeah, so maybe Joe can tune in on this as well, because I think this is a common interest for the both of us. So you're touching on a very, on a fantastic sort of new area here, which is, for one, obviously image-to-image translation, which would be potentially, I mean, this has to be mathematically proven, obviously. This could be a differential privacy technique. There's very little work at the moment talking about generative networks and their usability for actually modifying images in place. But there is a mounting body of work which is working, I think, on synthetic data generation. So on learning distributions in a differentially private fashion and using them to generate new training examples or representative new instances. And I think that this is a very promising and an interesting path for research. So Joe may want to comment on this as well.
Yeah, because even aside from the research perspective, I always like to have the whole spectrum of how that can land into industry, because I think that can be interesting for your audience as well. If you think of how a federated learning network might work in practice, you might have a data scientist that comes with his own model but doesn't have any data. So in a way, he needs to bootstrap the model one way or another, and making this synthetic data available, at least to bootstrap the models before training on the actual data in a federated fashion, might be a very interesting combination of the two approaches, I think.
Great. I think that's a very interesting approach to that you just proposed. Thank you. Oh, Sophia, you're on mute.
Thank you. And I want to ask another question that came from our participants when they're registering. So we had a really interesting questions about the ethical consideration when it comes to using AI diagnosis in low-income countries. Would you be able to discuss a bit about on that?
Yeah, and this is something that's actually really, really close to my heart, because we're working on exactly these kinds of solutions, and I think it's extremely important to offer them, especially in this kind of scenario. So I think that this is a fantastic way to provide privacy preserving AI is a fantastic way to provide medical diagnostic services in the form of a inference as a service scenario, for example. And to do this kind of thing, one would obviously need to ascertain end-to-end privacy and optimally also end-to-end encryption. And the good thing is that the democratization of these techniques will allow this kind of usage also in low-income areas. So this is one sort of aspect of it. The other aspect of it is that we can also make sure, using these techniques, that there is no exploitation going on from the side of the algorithm owners. So we can ascertain on a system level that there's ethical and moral boundaries to the usage of the algorithm. And that's maybe I can throw in a term, it's called single-use accountability. So you make sure that the algorithm and the data are being used for one thing and only for one thing, and for nothing else, for example, benefiting another model without, you know, the participants actually having knowledge of it or profiting from it.
Great. I think we're going to hazard a last question before wrapping everything up. So someone in the chat asked if you could elaborate a little bit on the topic of privacy budget and how to pick parameters for it, how to communicate to end users, especially in consumer applications. So maybe a couple of words on privacy budget.
Yeah, so I can start. Maybe Joe, you can tune in as well of this. So privacy budget is, as we mentioned, a term coming from the field of differential privacy. There is various sorts of differential privacy. Maybe we should mention the two most common. One is epsilon differential privacy. That's the Greek letter epsilon. The other one is Rennie differential privacy. And both come with this idea of a privacy budget. And I think the simplest way to explain it is to talk about how much interaction do you have left with the database before I prohibit you from making any more queries because you've used up your budget. And the reason for that is that with every additional query, you might be able to use the information that you gain from the statistical mean or another statistical metric of the data set to distill more information about individuals. And this is exactly what differential privacy is about, to protect the individual while allowing inferences about the mean or about the, you know, the entire data set. I know, Joe, do you want to add anything to this?
Yeah. So it's picking the right epsilon is extremely challenging. Please do reach out offline, or we can make some documents available as well. There's quite an interesting body of literature that's either try to come up with techniques automated to tune your privacy budget depending on the applications you want to do, or we ask for more transparency because it's also sometimes something that is not really disclosed in some studies. So it can be a very sensitive piece of information.
Okay, great. And so as we wrap up, I just want to thank everybody for joining us today and the presenters for sharing their thoughts and their ideas and the paper that they just published. We're going to send an email to everybody who registered for the webinar with the recording of the webinar, as well as the resources that we mentioned during the session. But before we go, I want to ask one last question to our presenters. And it's a very broad and general question. And I'm wondering, what can people do right away to make their systems more secure or more privacy preserving until we're ready for these next generation methods to kick in a widely implementable way?
So I think what you said is, like, you know, use PySift. So I think join the open mind community. That's certainly a good idea. I think more generally, one could say, you know, get informed. That's really important. Start understanding what private data you're handling, how sensitive the data is you're handling, and how sensitive the stuff you're doing with your data is. So I think that's very important. Then make sure your systems are safe and secure. So there's little sense in having differential privacy if you're hacked and your data gets stolen. And you know, get informed about the new contributions to the whole ecosystem and follow up. I think that these are the best suggestions, and of course participate in the discourse. This is open to anyone, and it's a very open and welcoming community. So we welcome everyone, even people who really don't know anything about privacy preserving ML yet.
And also, even oh, sorry, Rikma, go ahead if you.
Go ahead, Jonathan.
No, I wanted to, like, you don't have to be technical. We also need, like, people with knowledge in legislation, for example. Like we've discussed the impact of GDPR and HIPAA. There is something that I think is quite concerning. A piece of encrypted data is still considered sensitive information, whereas a piece of anonymized data is not. And I think in the literature, we have proofs that the former is more secure than the latter in terms of the ability to re-identify the original piece of data. So we need people with legal background, people with access to the deciders to make the legal framework evolve at the same breakneck pace as the tech is evolving.
Yeah, I think from a very simple answer to this would be, from a medical point of view, is really get the expert in-house. Don't sell out, don't sell your data to companies. Keep the data safe and have experts deal with privacy issues. I mean, just take it serious, because as George alluded to in the very beginning, we're always prone to think that anonymization is fine, and then we can send the data off. But you all know, or at least people who are, or at least radiologists who know to read images, know that this is for sure not the case. You recognize, even human beings can recognize patients they've seen before just based on the image. So this is something very intuitive, and I think, yes, having this interconnection between these experts and the medical field is really essential, not only to keep it private, but also to develop these techniques.
Super. Thank you. Thanks, everyone. We're going to wrap it up. If anybody has any questions for the presenters that they still want to ask, I encourage you to stay on the line. A few of them will be available for another few minutes to answer your questions. Otherwise, we wish you a very good day, and keep an eye out for our next webinar in a month or so. Thanks, everyone.